Hello everyone, welcome back to Mr. Lee's Math Class Videos YouTube channel. I'm Mr. Lee. We're in Math 0332 today, picking up in our bonus unit, which just has 2 homework assignments over scientific notation and multiplying binomials, which is like the FOIL method. So let's go ahead and pick it up. So scientific notation is a way to represent numbers where you're given a number which is really a number with potentially decimals, but to only one place in front of the decimal, so a ones place and some decimals, and then times 10 to some power to tell you how many times the decimal would need to be moved to get the true number. An example of this would be 1.3 times 10 to the third, which really means when you have a positive exponent here, that decimal would be moving 3 places to the right to get it back to normal notation. A negative number means you need to move the decimal to the left. So that's really it. So 1.3 times 10 to the third means you would move it 3 places to the right. And any place that doesn't have a number, you would put a 0 in, so it would become 1300. 2.7 times 10 to the negative fourth means you're moving it 4 places to the left. And again, you're putting in the zeros where they go. So it would be 0.00027. So we're just going to practice doing a few of these, and I'll leave some for you to do. 3.9 times 10 to the 7th really means we're taking 3.9 and we're moving the decimal 7 places. Put in the zeros for all the places you don't have. So this is really, let's see, 6, 39 million. Generally speaking, 1,000 would be times 10 to the third. Million is times 10 to the sixth. So really, this is one more 10 than that, so it's 39 million. And then billions would be 10 to the ninth, in case you care. 5.8 times 10 to the negative second. We take the 5.8, we move it twice to the left. So this should really be 0.058. And I'll leave number 3 and 4 for you to do. I don't really think people have much difficulty converting. What about going the other way, converting the numbers to scientific notation? Let's look at that on the next page. So if you're going from decimal to scientific notation, you're really trying to find where the first non-zero number is and how far you have to move the decimal to get there. When you were going from scientific notation to decimal, moving to the right, positive numbers cause you to move to the right, negatives move to the left. Here, since we're moving back to scientific notation, we're effectively undoing what happened on the last page, which means if you need to move the decimal to the left, it's creating a positive, and if you need to move the decimal to the right, you create a negative. Generally speaking, something that's bigger than 1 should have a positive exponent on the 10, and something that's smaller than 1 will have a negative exponent on the 10. So looking at 750,000, if I wrote this with a decimal, it'd be 75000 and then point. So I have to move this 1, 2, 3, 4, 5 to get it to the number. That's just one number in front of the decimal, so 7.5. And sometimes you can ask yourself, how would I get from here to here? I have to move it 5 to the right. This is really times 10 to the 5th, because we moved it 5 to the left. But again, this number is bigger than 1, so it should be positive. Number 2 is kind of similar. It needs to move 4 to the right. So you would get 3.2 times 10. And because we moved it to the right, this one gives you negative 4. Furthermore, this number is below 1, so it should have a negative exponent. If you just need to move it one place, like 86.2 is really 8.62 times 10 to the first. 0.175 times 10 to the 7th. If it's already kind of in scientific notation, but you have a number that's not already like it, then you just need to figure out what you need to move that to. So this becomes 1.75, and since we move it 1 to the right, times 10 to the negative first, and we'll just bring this down. And this is why we have already done the exponent portion of this. What happens when you're multiplying with the same base? You add the exponents. This is 1.75 times 10 to the 6th when we properly get it back into the right form for scientific notation. Now we also have operations between numbers with scientific notation. It's going to work a little bit like operations in our exponential sections. If you're multiplying with the same base, you add exponents, and then you'll multiply the numbers in front. If you're dividing, you'll divide the numbers in front and subtract the exponents, and then convert as needed if it's not in proper scientific notation. So here, 4 times 2 is 8. 10 squared times 10 to the negative 5th is 2 plus negative 5. So we add the exponents. This is really 8 times 10 to the negative 3rd. And this is leave your answer in scientific notation, so we're not going to simplify this at all. We just leave it like that. Number 2, 9 divided by 3. Since we're dividing, we will subtract exponents. 5 minus 4, so 9 over 3 is 3. 5 minus 4 is 1, so this is 3 times 10 to the first power. Sometimes you need to do some multiplication or division. My suggestion is to convert them to scientific notation. So this one is what, 4.3 times 10 to the 4th. This one goes the opposite way. It's 5 times 10 to the negative 3rd. And now we can multiply them the same way we just did there. 4.3 times 5. That might require a little bit of skill. I'll tell you that this is 21.5. And then adding the exponents, 10 to the 4th plus negative 3rd. So it's really 21.5 times 10 to the 1st. But there's still a problem here. 21.5 is not how numbers in scientific notation are supposed to be labeled. So here I need to move the decimal 1 to the left. So this is really 2.15 times 10 to the 1st. And then bring down this other 10 to the 1st. And so this actually ends up being 2.15 times 10 to the 2nd. And I'll go ahead and leave number 4 for you to do. The last set of things is the multiplying binomials. So for most of you, you've heard of FOIL before. That means if you have 2 things in a parentheses times another 2 things in parentheses, each one multiplies towards the other one, and the operation in the middle is kept. They're often referred to as FOIL, where you multiply the first number in each group, then O outer, the outer numbers, I inner, the inner numbers, and the last number in each group, and then you would add or subtract them all together. This is mostly done with algebraic terms. So x plus 5 times x plus 2. First would be x times x, which is x squared. Outer is x times the 2 on the outside, which is 2x. Inner, 5 times x, which is 5x. And last, 5 times 2, which is 10. And you just add them all together. X squared plus 2x plus 5x plus 10. When you do this, most of the time your middle terms should combine. So this should be x squared plus 7x plus 10. So 2 is similar. I want you to practice 2 in this method because we have more on the next page that we can talk about. It doesn't matter if there's numbers in front of your x's. It works the same. So I want to look at number 4. We'll do it again. First, 4x times 7x, which is 28x squared. Outer, 4x times negative 3 is negative 12x. Inner, negative 7 times 7x is negative 49x. And last, negative 7 times negative 3, which is positive 21. So this is 28x squared minus 12x minus 49x plus 21. And again, our middle 2 terms combine. 28x squared minus 61x plus 21. Let's also do one more, 5 or 6, so we can talk about what it means to be squared. If you see something like this raised to a power, that means something times itself a total of 2 times. So let's say the 3x plus 2 times squared really means 3x plus 2 times another 3x plus 2. And then you would use that same strategy for foiling. So we'll do, the only thing is that when you're doing something squared, the first of both of these things should be the same. 3x times 3x. The outer and the inner will also end up being the same. One is 3x times 2. The other one is 2 times 3x. So it gets you 6x and 6x. And then finally last, in this case, is 2 times 2, which is 4. So you get 9x squared plus 6x plus 6x plus 4. And again, you combine your middle terms, 9x squared plus 12x plus 4. And that's really all of the material that there is in this entire course. So I hope you've had a good time with it.